A measurement made by a fluorometer is unique to the individual instrument and is the fundamental difference between absorbance and fluorescence measurements. The spectral correction data program is used to correct and eliminate artifacts in a sample spectrum inherent to an individual spectrophlorometer's emission and excitation monochrometers. Fluorescence is directly related to the luminous flux and efficiency of measurement, and to perform accurate spectral measurements, references are created to known calibrated materials. These calibrated sources are checked for absolute spectral output on a known instrument, and a reference spectrum is then supplied to correct the individual instruments. Correction of the excitation and emission monochrometers can be performed using rhodamine B, a calibrated tungsten iodide light source, and a calibrated deuterium light source, or a calibrated detector. The source used to calibrate the monochrometers will depend on the wavelength region being probed. In this video, we will use rhodamine B and a tungsten calibrated light source to correct the excitation and emission monochrometers respectively. We will also illustrate how to indirectly correct the excitation monochrometer with the calibrated light source. Rhodamine B can be used to create correction data directly obtained by the excitation monochrometer and indirectly by the emission monochrometer between 200 and 600 nanometers. The tungsten iodide calibrated light source directly corrects the emission mono and indirectly the excitation mono between 350 and 1010 nanometers. A calibrated deuterium light source is also offered for the UV region. Since quantum yield measurements require integrating spheres, this correction data will be obtained with an integrating sphere. However, spectral correction can also be performed with the standard cell holder. The accessory used to measure the sample spectrum to be corrected must match the accessory used to obtain the correction data. This video will demonstrate how to perform a spectral correction for a specific sample with the intention of later performing quantum yield calculations. For example, our sample's excitation and emission wavelengths are 370 nanometers and 350 to 700 nanometers respectively. We will therefore only be obtaining corrected data for the excitation monochrometer between 300 and 400 nanometers and the emission monochrometer between 350 and 700 nanometers. However, since the wavelength range is only limited by the selected source, spectral corrections can also be performed for a wider wavelength range to cover a variety of samples and wavelengths. The spectral correction procedure will vary slightly for each calibrated source and accessory used, but the spectral correction software will walk you through each step. Double-click on spectral correction data to open the measurement program. When you first open the program, a preview of the last selected spectrum will be shown in the spectrum window. You can select the available datasets to view by specifying whether you wish to view excitation or emission correction data and filter by the bandwidth and accessory. If this is your first time performing a spectral correction with a calibrated light source, you will first need to register the pattern file for said source. Go to Settings, Pattern File, insert the CD-ROM, and click Add. Click Open and then select the pattern file from the CD-ROM. Then click OK. To create a new correction file, select New from the Data menu. We will start with the emission correction data using the tungsten calibrated source. The emission bandwidth used for measuring the sample spectrum is 5 nanometers, so the bandwidth needed to correct said sample spectrum will also need to be 5 nanometers. For spectral correction to work effectively, it has to be performed at each instrument parameter and bandwidth combination. So the spectral correction at a 5 nanometer spectral bandwidth cannot be applied to a measurement using a 10 nanometer spectral bandwidth. This also applies to position of polarizers if they are being used, as well as the use of higher order filters. After selecting OK, the program will walk you through the steps necessary to correct the data. The first dialog box specifies the setup using the selected accessory and calibrated source. Place the white standard plates in the excitation light inlet and indirect excitation ports, turn the light source on, and select Next. Specify the emission wavelength range and a starting sensitivity. To verify the specified sensitivity is appropriate, select the Preview button. Now click Measure. The sensitivity should be set to obtain the maximum fluorescence intensity in the desired wavelength range. Since spectral correction only corrects the spectrum shape and not the intensity, the spectral correction sensitivity selected does not need to match the sensitivity parameter used to obtain the sample spectrum. You may need to test out a few different sensitivity parameters before you find the optimal one. If the signal saturates at any of the sensitivities selected, decrease the sensitivity. Once the optimal sensitivity parameter has been selected, close the preview box, enter or verify the sensitivity parameter in the measurement box, and select Measure. When the measurement is finished, select the pattern file of the calibrated source you registered earlier and click Next. Choose the peak wavelength to normalize the spectrum on. Again, since the program corrects the spectral shape and not the intensity, the normalization wavelength is not critical. Just select the peak wavelength for consistency, then click Next. To save the emission correction data, enter the desired information in the text boxes and click Complete. To perform the excitation correction using Rhodomine B, go to Data New and select Excitation and Rhodomine B under Correction Data and Method respectively. The excitation bandwidth used to obtain the sample spectrum that will later be corrected is 5 nanometers, so the bandwidth for the correction data is set to 5 nanometers. Select OK. Prepare for measuring the excitation correction data by placing rhodomine in the sample setting port. Keep the white standard plate in the indirect excitation port and insert a 3 mm aperture in the aperture holder of the integrating sphere. Make sure that if the tungsten calibrated light source is still connected, the light source has been turned off. Then select Next. Specify the excitation wavelength range in a starting sensitivity setting. Click Preview to make sure the optimal sensitivity has been chosen, as you did for the emission correction data. Once the sensitivity has been selected, click Measure to obtain the excitation correction data. Now select the wavelength to normalize the spectrum on, click Next, and save the Rhodomine B excitation correction data. The excitation monochromator can also be indirectly corrected using the calibrated tungsten light source between 350 and 1010 nanometers. Indirect correction data can only be created by measuring or opening a previously measured companion correction data file. To correct the excitation spectrum using the calibrated tungsten source, select these parameters in the New Correction dialog box. Click Browse to select the previously corrected emission spectrum using the same calibrated light source. Once the emission spectrum has been selected, click OK and verify the standard white plates are in the necessary positions and that the light source is on. Then click Next. Specify the excitation wavelength range and click the Preview button to optimize the sensitivity parameter. Once the sensitivity parameter has been selected, click Measure to obtain the excitation correction data. Select the wavelength to normalize the spectrum on, click Next, and save the calibrated tungsten light source excitation correction data.